Let us solve a turbine problem. Problem 4163 from the problems module of test using the PC model. We'll carry out an energy and entropy analysis, solve the problem manually, and compare our results with the results from TestCalc. Let's see what's given in the problem. Inlet conditions are specified, which we'll call state 1 here. And the exit pressure is given and we are supposed to find the maximum theoretical power, which means the exit state must be ideal state, isentropic state, and also we'll call the actual exit state as state 3 when the turbine is not isentropic. We have solved this problem already using the PG model on a separate solution. And I'm going to write down some of the results we got from that solution so that we can compare later when we solve this problem by using the PC model. So the ideal work output of the turbine when you use the PG model was found to be 4263, and the actual output for the PG model was found to be 3549, which resulted in a turbine efficiency, which is W.T, the smaller one, actual by ideal, to be about 83.2%. So if somebody just took H2O as a perfect gas, solved the problem blindly, this is the answer they would have gotten. Now we'll go out and use PC model to solve the problem in a comprehensive manner. So the first step is what? To draw this, transfer this problem into a TS diagram. As you recall, in the TS diagram, there's a dome shape region that separates superheated vapor from mixture and subcooled liquid. So we'll draw a constant pressure line corresponding to the high pressure at the inlet, which is the 4 MPa line, and we'll also draw the exit pressure line. So this second line, this line corresponds to 200 kPa, and this is 4 MPa. So you know the inlet state 1 must be somewhere along this top line, and the exit state somewhere on the lower constant pressure line. So to figure out where state 1 is, let's write down what we know about state 1 first. Pressure is given to us 4 MPa, and temperature is given to us 600 degrees Celsius. So the first thing to do is to find the saturation temperature at 4 MPa, and if T sat at 4 MPa is lower than 600, then obviously our state will be superheated. So let's first find what is the saturation temperature at 4 MPa. For that we go to the table. Let's go to property tables, PC model. Table B is the PC model, and to find the saturation temperature you could go to PSAT, but we know the turbine inlet probably is going to be superheated. Another tricky way of finding the saturation temperature is directly go to the superheated table, and our pressure is 4 MPa. So go to the 4 MPa table, which is right here, and in the 4 MPa table you will notice the saturation temperature is listed right in parentheses next to the pressure, which is 250 degrees Celsius. So clearly, if this is 250 degrees Celsius, then 600 degrees Celsius might be way up here. So this is our state 1. Superheated. So let's pick up what is enthalpy and entropy. So at 600 degrees Celsius, the enthalpy is 3674 and entropy is 7.369. So let's write those down. And again, they're all SI units, so I'm not going to write the units down to save time. So enthalpy and entropy at state 1 are known. So how do we figure out state 2? We know state 2 is isentropic because it's an ideal for an ideal turbine. Entropy doesn't change. You can show that from an entropy balance equation. So state 2 will be somewhere here. Well, in this diagram, it shows as if state 2 is superheated, but we should not assume it's superheated. If suppose state 1 were here, then state 2 would end up as a mixture. So let's keep our mind open. So to find state 2, we'll first list what we know for sure. The pressure is known, 200 kPa, and the only other thing that is known about state 2 is entropy is given to us, which is equals S1, which we calculated to be 7.369. So now that we know entropy at state 2, we'll compare entropy there with the F and G point entropies. So let's find out what is SF at 200 kPa and SG at 200 kPa. So our strategy is that suppose we find that the entropy at 2 is in between these two values, then of course we will have a mixture. On the other hand, if S2 is higher than SG, then obviously we'll have a superheated vapor. So let's find SG at 200 kPa. To do so, this time we have to go to the saturation table, and 200 kPa, so we choose the pressure. We choose the pressure table because in pressure table, the pressure will appear as the first column. We know 200 kPa, which in MPa is 0.2. And if you look at what is SG value, it's the last column, 7.127. So we go and write that down. This is 7.127. And what is the value of our S, if you recall? 7.369. So 7.369, which is greater than S2 is greater than SG. So therefore, we don't have to even find SF. State 2 must be superheated because S2 is greater than SG at 200 kPa. So our conclusion, we have a superheated state for state 2. So now we can pick up the enthalpy quite easily. We go back to the superheated table. And go back to the 200 kPa, which is 0.2 MPa line, and look for entropy to be 7.369, and which is somewhere in between these two lines. So if somebody asks what is exactly the temperature or enthalpy, we're just going to eyeball it because we'll see that even eyeballing will get pretty good answer. So 7.369 is our entropy we're looking for, which is in between these two. Let's just kind of take an average. So we'll say, okay, enthalpy is somewhere between these two. So we'll just 2800, temperature will be 175. So we'll write enthalpy to be 2800. I know it's not very accurate. And temperature to be 175 degrees Celsius. Not that we need the temperature, but it's good to know. So this is our approximate enthalpy value for state 1, and we have also calculated state 2 and state 1 completely. So now we can do a turbine analysis, but before we do so, let's go and verify these states using test calc. Okay, so we go launch test calc, system analysis, open system, open steady system, generic, and a single flow system because there is only one inlet and one exit in a turbine, and finally PC model. And you have to select the launch test calc tab, and we got the test calc going here. H2O is already selected as the fluid. Let's enter the pressure to be 4 MPa, and temperature is given as 600 degrees Celsius. We also know the mass flow rate, so state 1 is calculated. And the enthalpy found is 3674, which is pretty close to which is exactly what we got from our table. State 2, pressure is supplied, and we know it's isentropic to state 1 for an ideal turbine. S2 equals S1, and of course mass flow rate is the same. Notice I always use equations as much as possible instead of hard numbers. Now, it's always a judicious thing to do to draw the TS diagram as soon as you calculate states to make sure things make sense. So if you draw the constant pressure lines, notice because we find state 2 to be higher than state 1. So this can be a teachable moment. What mistake we did? Obviously state 2 we expect to be lower than 1. Look, the pressure at state 2, instead of 200 kPa, I entered that as 200 MPa. Big mistake. So when I do 200 kPa and calculate, notice now state 1 is up there and state 2 is down there because we know the pressure is lower. So that's the value of drawing the TS diagram. If there is a mistake, it graphically shows up instantly. Imagine in a more complex problem. So you have to learn how calculated states maps into a diagram such as the TS diagram, very widely used in thermodynamic analysis. Okay, so that let's verify the enthalpy we got is 2808 for state 2. Again, our eyeball calculations was what, 2800, very close. Now that we know state 1 and 2, we can go and find the ideal turbine output in an instant. W dot turbine ideal, and this time is for PC model obviously, M dot H1 minus H2, which is 5. Our H1 was 3674 and H2 was 2800, and that gives us approximately 4370 kilowatt. So what is ideal from test calc? Let's verify. Go back to test calc, device panel, and state 1 is the inlet and state 2 is the exit. No heat transfer. 4328 is the answer. Now, some may think that our manual solution is pretty bad compared to the more refined calculations. But if you think in percent term, it's well within a couple of percent. So this answer is very, very acceptable in the engineering world. Okay, now the last thing to do in this problem is to go find state 3. And what are known about state 3 is the pressure must be same as state 2, and the temperature is supplied 220 degrees Celsius. So if you go back to our TS diagram, we know, where is our TS diagram? Here. State 2, we got a temperature of 175, is the same pressure, and now we have a pressure that is even higher, a temperature which is even 220 degrees higher, so obviously state 3 will be up there. We also know in an actual turbine, entropy is generated by friction, so we expect entropy to be higher at 3. So for both reasons, in an actual turbine, state 3 will be to the right of state 2 on the same pressure line. So this is obviously superheated vapor because state 2 is already superheated vapor. So to find the enthalpy and entropy for this state, we go back to the tables, and this time, yes, it's already 200 kPa table right here. And for 220 degrees Celsius, which is between 200 and 250, let's pick up the enthalpy to be somewhere in between 2870 and 29, let's say 2900. And entropy would be maybe 7.5 and 7.7, let's say 7.6. We're just eyeballing it. So we conclude that enthalpy is 2900 and entropy is 7. What did we decide? Sorry. 225 was the 220 is the temperature, 7.6. Yep. So therefore, now that we know state 3, we can calculate the actual output of the turbine. M dot H1 minus H3. H1 is 3674 and H3 we just now estimated to be 2900, and that gives us about 3870. The turbine efficiency therefore is actual output by ideal output is 3870 divided by approximately 88.5%. That's our manual solution. So what is our W.T actual in using test calc? Well, for that we go back and to the test calc and calculate what would be state 3. For state 3, the pressure remains the same, P2 and P3 are equal, and temperature is supplied to be 220 degrees Celsius, and of course mass flow remains the same. So we know state 3. Again, it's not a bad idea to calculate and show that the constant pressure lines 3 is to the right of 2. 1 and 2 are vertically aligned because entropy remains constant. This is the entropy scale. And 3, the entropy is a little bit higher because entropy is generated inside the turbine. Going back, so we found the enthalpy here to be 2910, which is pretty close to our manual solution of 2900. And finally, in the device panel, we go select a different device, a device B, as the actual turbine. State 1 is our inlet, and state 3 is our exit. No heat transfer. The turbine is adiabatic, insulated, and 3818 is our external work. So notice for device A it was 4328, and for device B it is 3818. So if you want to find the efficiency in the I/O panel using the calculator, efficiency equals, we just start with an equal sign to evaluate any expression. 3818 divided by, what was the 3818 is our actual output, and ideal output was 4328. We go back 4328, and the efficiency is calculated 0.882, which is 88.2%. So eta T test calc. So notice how close they are. So our manual solution is quite good. Well, if you recall that the ideal work output of 4370 or 4328, whichever you pick, is way different from the ideal output obtained from the perfect gas model. You may say, well, it's not that different. It's, we got a turbine efficiency of 83.2% using a very crude perfect gas model, and it's 88, so it's not totally out of the range. But remember, in this particular problem, the steam happens to be superheated vapor both at state 1, in state 1, 2, and 3, in all the states. So when a phase change fluid is in the superheated form, it is more akin to a perfect gas. Essentially, what is a gas? Gas is a superheated vapor which is way, way superheated, far removed from the dome region, in the superheated region. So if the steam is very highly superheated, the PG model will do a better job. But imagine if the steam happens to be at state 2 or 3, there could be condensation, there could be a quality involved. So if you have a mixture of saturated liquid and vapor at state 2 or 3, then we'll have a big problem if you ever use perfect gas model for that. So this is just an academic study. For a phase change fluid, you are supposed to use the PC model for an accurate answer, and PG model is simply not acceptable.